we had just shown that that Euclidean space is complete, right? And there's one more thing that we want to get to. It's called the monotonic sequence theorem. Okay, so monotonic sequence theorem. Okay, so this. Okay, so start off with a simple definition. You have some sequence, Sn, a sequence in R, a sequence of real numbers, and you know that so if they are increasing, right? Like if S sub n is less than or equal to S sub n plus 1 for all n, then we say that the sequence is monotonically increasing. Monotonically increasing. Okay. So you see that this less than or equal means that it's really non-decreasing, right? It could be constant, right? You could have a constant sequence. But we call this sort of thing increasing, and usually when we want to say that it's truly increasing, like it can't be constant, then we say strictly. We'll say strictly increasing. Okay, and then similarly for decreasing. Okay, so then there's this theorem about monotonic sequences. Theorem about monotonic sequences, and it says that if you have a monotonic sequence, then Sn converges if and only if Sn is bounded. Okay, so convergence is equivalent to boundedness for monotonic sequences. Okay, so I'd like to hear what you think about this. What about convergence implies boundedness? If it converges, then it implies bounded. What do you think about that? Convergence implies boundedness. Does that seem reasonable? Why? Somebody explain to me why? Why that makes complete sense. If you have a convergent sequence, right? So there's some number, right? There's some number that you get arbitrarily close to, right? There's some number that you get arbitrarily close to, right? And so you say, I want everybody to stay within 1 of that number. I want everybody to stay within 1 of that number. Then you know that past some time, everybody does that, right? So those guys are bounded, and then like we said in a previous argument, you have only finitely many other guys, and you can bound those guys as well. Okay. Yeah.
Doesn't it have to be monotonically increasing, so it's not like L plus 1? It can only be like underneath L.
So that's good. In my picture here, I don't necessarily have a monotonic sequence.
Okay.
Right? So I have something like this. It's just an arbitrary sequence. Okay. So what what you're noticing, I think, or at least you're sort of pointing out that I'm not talking about a monotonic sequence here.
Okay.
And that's because
I know you said S.
That's right. That's right. So the reason I'm not talking about a monotonic sequence is because it doesn't have to be monotonic for this to happen.
Got it.
Okay. So convergence implies bounded. It's true for any sequence, monotonic or non. Okay. So this is always true. This is true converges, it's going to be bounded. Okay. Now in the opposite direction, yeah, no, the picture is wrong. Right? And now what we have is a sequence that is monotonic and bounded. Okay, so there's some bound. Anyway, there's some bound up here, and we have a monotonic sequence. Okay, here's some monotonic sequence, and we're saying that that's got to converge. Okay, that's got to converge. Does anyone see why that's? Can anyone give a reason why that's going to happen, or what do you think it's going to converge to? What do you think it'll converge to? Read.
The bound.
The bound? What if this, what do I say? This is my bound.
Supremum.
The supremum. The supremum, yeah. So take this, so we know there's an upper bound to all the values, right? So since the set of values has an upper bound, we know there exists a supremum of all those guys. Right, so let's write it like this, so then we don't get confused between the set and the sequence. Since the set E being S1, S2, S3, etc., has an upper bound, it has a supremum. And let's call it supremum gamma. And we claim that Sn converges to gamma. Okay, so there's some supremum gamma, right? We claim that it converges to gamma. Why does it converge to gamma? Well, suppose we wanted to stay within epsilon of gamma. Suppose we wanted to stay within epsilon of gamma. How do we find a time past which everybody stays within epsilon of gamma? Adam?
You just find one point that does fall in that area, and you can
Everything
that neighborhood.
afterwards.
Sorry,
Yes.
and then you can pick every point after that.
That's right, that's right. So you say, well, look, since this is the supremum, we know that within any neighborhood, there must be one of these guys, right? Otherwise, this is not the supremum. You know, we've seen this argument, maybe even on your exam, right? Right. So, given any epsilon, there must be the interval gamma minus epsilon. Gamma must contain some Sn, right? Else it's not the supremum. Right? Let's call it S sub capital N. Okay. But then, since you're increasing, right? So you know that there's somebody at some point. You enter that neighborhood, but then since it's an increasing sequence, past that point, everybody stays in that neighborhood, right? Since it's an increasing sequence, and since gamma is the upper bound, right? Then everybody stays between gamma minus epsilon, right? So for n bigger than n, we see that S sub n is bigger than or equal to S sub n. Which is less than or equal to gamma, and the S sub n, remember, is bigger than gamma minus epsilon, right? So, S sub n lies within gamma minus epsilon, gamma gamma. Right? So, and so that's what you need to show convergence, right? Right? You need to show convergence. You need to show that given any tolerance, there's a time past which that tolerance is satisfied. And so we found it. any questions about the monotonic convergence?
Why do we make the interval half open?
Because the S of n could be gamma itself, right? Yeah, S of n could be gamma itself. Like maybe it suddenly jumps to gamma and then stays at gamma forever, right? So I want to make sure that I get that. Right. If I guess I don't need to be so precise about it. I could just say this interval has to contain some S of n, but I know it's actually in the lower half of the interval, right? Because gamma is the upper bound. Yeah,
How about the E bond?
that we just use to show to get that the sequence has a supremum, right? That doesn't play into the theorem. As long as there's an upper bound, we know that the sequence is going to converge. Okay. 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 So let's go on to these things called limit inferior, limit superior. Okay. So usually called lim inf and lim sup, and sometimes written lim with an upper bar, lim with a lower bar, and lim with an upper bar. Okay. So usually we call them lim inf and lim sup. Okay. And so these are sort of modifications of the notion of limit for numbers. And they will be crucial, well, mainly the lim sup will be crucial when we start talking about convergence of series, convergence of power series. When you're doing convergence tests, then lim sup is really the key. You may remember when you were in Calc 2 and you did convergence tests, it would say, if this limit exists, then and this thing is greater than 1, then you have divergence, and if it's less than 1, then you have convergence. Blah blah blah. But it only worked if that limit existed. The good thing about these guys, we'll be able to get results along those lines, but the lim sup always exists, so you don't have to worry about it if it exists or not. So the theorems will say if the lim sup is bigger than this or less than this. So okay. So first we just for completeness, let's introduce the following notation. Sn, a sequence of real numbers. If, and this I think we said before, if for all numbers in R, they exist in N such that Sn is bigger than M for all n greater than N, then we write Sn converges to infinity. So this, I think we actually introduced this before, right? You have some sequence, it converges to infinity. It means that given any bar, there's a time past which everybody is above the bar, right? So you have some sequence, right? Given any bar, there's a time past which all values are above the bar. Yeah.
To be clear though, Sn converging to infinity means that it does not converge, correct?
So that's what we called it earlier, saying it doesn't converge. But for right now, we're going to call this a kind of convergence. We'll say it converges to. But
so
yeah.
Is this just like in the extended real number system? Is this in the extended real numbers or?
You'll see why we need it in a second.
Okay.
Okay. So when we define you'll see why I need it in just 1 second. Yeah. Just wait for 1 minute. Okay. So now let's define the notion of lim sup. So you have a sequence S of n of real numbers again. Okay. Now, let E be a subset, E be a subset of the extended real numbers. Okay, and similarly for negative infinity, you know what we mean. Okay, so let E, a subset of the extended real numbers, denote the set of all subsequential limits. Of S of n. Okay, the set of all subsequential limits of S of n, including infinity if you have a subsequence that goes off to infinity. Okay, so you have a sequence, and you look at all its subsequences, and if they converge to anything, if there's any subsequences converge to values, those guys are in your set D. And if you have a sequence that diverges to infinity, or however you want to say converges to infinity, you throw infinity in. You have a sequence that goes to a negative infinity, you throw negative infinity in. Okay, so the set of all subsequential limits. Then we define the lim sup of your sequence as the supremum of E. So it's the supremum of the set of subsequential limits. Okay. And similarly, lim inf of E is defined as the, lim inf of the sequence is the infimum of the set of some subsequential limits. Okay, so just to give a simple example, right, if S of n is -1 to the n, right, then the sequence doesn't converge, but it has a lim sup, right? The set of subsequential limits is just 2 points, -1 and 1, right? And the lim inf is -1, and the lim sup is 1. So lim sup of S of n is 1, and inf is -1. And you see that the lim sup is always going to exist, right? Because if infinity is not in there, right, then the set is finite, and it's going to have some finite. Then it'll have a supremum. If infinity isn't there, then infinity is the supremum, right? And so on and so forth. So, okay, any questions? Yes, E?
How about Sn is not converged to any point? Do they have the lim sup and lim inf?
So, how does it not converge to any point?
Like n squared.
Well, that will go to infinity then, right?
So
Right. So think like this: if Sn is bounded, right? If Sn is bounded, then what's going to happen?
it has the sup or inf. If the supremum or infinity.
If Sn is bounded, you know that there's going to be a convergent subsequence, right? This is what we showed last time, right? You have a compact set. You have this infinite number of points inside, right? If it has a finite range, then they repeat, right? You can get a constant subsequence. If there's an infinite number of guys, then you know that there's a limit point to that thing, and you create a subsequence that converges to that point. Okay, so if it's bounded, it's gonna converge. If it's not bounded, then it's gonna go to infinity, right? So, okay. Okay. So here was the problem that I was going to make you do. So X is a metric space in general. P sub n a sequence. And then the set of subsequential limits P sub n is closed. Okay. In other words, any limit point of this set is going to be itself a subsequential limit. Any limit point of the set is in the set, i.e. itself a subsequential limit. So what that would say is that, sorry, you guys are still writing. Okay, what that would say is that, well, if you look at the notion of lim sup and lim inf, these guys are, this is the supremum of the set, so it's a limit point. It's a limit point of the set, right? It's either in the set or it's a limit point of the set, right? And so what this would say is that the lim sup itself is a subsequential limit, right? That's what this theorem implies. That the lim sup is a subsequential limit itself. Right, and the lim inf is also a subsequential limit. Yeah.
Oh, never mind.
Okay. So should I let you think about it? This was going to be the warm-up problem for this class. You have a metric space, you have a sequence, you have the set of subsequential limits. And you want to show that any limit point has to be itself a subsequential limit. Okay, think about it for 1 minute or two and see if you can think of why that makes sense. Right? Why is a limit point of the set of subsequential limits have to be a subsequential limit itself? Yeah.
So I'm confused. Are we given that the set of subsequential limits of Pn is closed, or is that what we're trying to show?
Then.
Okay.
does somebody have some sort of intuitive idea of why this ought to happen? Right? You've got a set of subsequential limits, right? And then you've got this point that is a limit point. You've got this point that's a limit point of the set of subsequential limits, right? And you want to show that you can make a subsequence of these guys that actually converge to P, right? So nearby are these other guys, let's call them L's, right? These guys are subsequential limits, and each of them is the limit of some subsequence, right? Each of them is the limit of some subsequence, right? So it seems pretty, maybe it's clear. Right? This guy is a limit point of the set of subsequential limits. Well, being a limit point means that every punctured neighborhood contains somebody from E, right? So every punctured neighborhood is going to contain some subsequential limit. Now, this being a subsequential limit means that you've got some subsequence of the P's, Pn I, Pn, Pn2, Pn3, blah blah blah, that converge to L, right? And so it's just a matter of sort of good bookkeeping to make sure that you can create a sequence of you can take a sequence of increasing guys from P that approach this guy P. Okay, does that make sense? Right. So let me write that out maybe more plainly. So you have this guy who's a limit. So say for epsilon sub n being, say, 1 over 2n plus 1, there exists a subsequential limit L sub n that lies in that epsilon neighborhood of P, right? So there's somebody in E who lies in that epsilon neighborhood of P. So I've got my P here, and I'm going to take shrinking epsilons, right? Epsilons that shrink by half every time. Okay. Right? So, right, here's L. Right? There's going to be some L1 in here, there's going to be some L2 in here, there's going to be some L3 in here, and so on and so forth. Right? So I take a sequence of subsequential limits that approach P. But then I know that I've got subsequence that approach each of these subsequential limits, and then I just create a subsequence that I pick guys that get close to P. So okay. So choose the L's, right? Choose these subsequential limits that are approaching P. Further, there exist infinitely many P sub n in the epsilon n neighborhood of L sub n. Here's L1, say, right? And I take the same epsilon neighborhood around L1, and I know that there's infinitely many P sub n's in there, right? And then I divide everything by half, right? So there's an L2 inside here. I take the half, the halved neighborhood of that guy. I know there's infinitely many guys there. And I keep on doing it. There's an L3 here. There's a half neighborhood here. There's infinitely many guys there, and you see what's going to happen, right? Right. So we can find an increasing sequence n sub k such that P sub n sub k lies in the epsilon sub k neighborhood of L sub k. right? But what's the distance of P sub n sub k from P the center, from P that limit point? Well, it's controlled by the sum of the distance of P sub n from P sub n k from LK, and this is LK from P, right? So the distance to LK plus the distance from LK to P, but that is epsilon, that's 2 epsilon k, right? The 2 epsilon k is 1 over 2 to the k. Right? And so we have the sequence that that converge to P. Right, so P is itself a subsequential limit. So, like we said, for us, that gives us the following fact, right? That given any sequence, then we know that the lim sup of the sequence is itself a subsequential limit. Okay. Any questions about that proof? Yeah, read.
Can E be finite?
Can E be finite? Yeah, why not?
So then would there be any points P in, there would be no limit points in P?
That's right, but then that set would be closed because it has no limit points. It contains all of its non-existent limit points. Right, a single
Yeah.
point is a closed set. Okay, so I've just said something that the lim sup of S of n is in E. I'm kind of cheating you here because this, when we talk about the subsequential limits here, we're really talking about, we're not talking about the things that we just threw in the case of the extended reals, right? The plus infinity and minus infinity. So, let me fix that. So, proof of one. Proof of one. Right? If the lim sup is finite, then it's in E by the previous result. If the lim sup is infinite, is plus infinity, then E is not bounded above, right? But if E is not bounded above, that implies that the sequence S sub n is not bounded above. So there exists a subsequence going to infinity. Okay, and then if the lim sup of the S sub n is negative infinity, that means that the set of subsequential limits is just the set negative infinity, right? If the lim sup, right, remember the lim sup is the supremum of the set of subsequential limits. If that's negative infinity, right, that means that the set itself is just negative infinity. But then you immediately have, there exists SNK going to negative infinity, right? Because this says that negative infinity is a subsequential limit at the end. So we do need to throw in those cases because the lim sup is allowed to include positive and negative infinity and not just what we previously called subsequential limits. Okay. Okay. So I've written it sort of in a bad way, but let me rewrite it. So I'm going to squeeze in a little bit here. So given any sequence, then there's two things that you can tell. Two things you can say. The lim sup of the sequence is a subsequential limit. And number two, given any number, actually let me write it this, yeah, okay. Given any number bigger than the lim sup, there exists an n such that n bigger than n implies that Sn is less than x. Okay. And I can say further, these two properties uniquely characterize the lim sup. Okay, so lim sup is actually the number with these two properties. Okay, this is another way of describing the lim sup. It's the number that is a subsequential limit, and it has this property here. Okay. This property here looks sort of funny, but it's actually should be kind of familiar to you. Here's what it says. It says that given any, let me write it with an epsilon instead of an x. Given any, so rewriting 2, given any epsilon, there exists an n such that n bigger than n implies that S of n is smaller than lim sup S of n plus epsilon. Right? So I'm just replacing x with lim sup plus epsilon. Right? And so this should look kind of familiar, right? This looks kind of like the definition of the limit. Right? This looks kind of like the definition of the limit, except we're sort of removing the lower half of our control. Right? What we're saying is that lim sup is this number. Lim sup is this number, and it has the property that given any epsilon, there's a time past which everybody's underneath this bar. Right? Everybody's underneath the epsilon, underneath this epsilon bar. Okay. And lim inf will have the same thing, right? It'll be the opposite, right? Given any epsilon, there's a time past which your all values are above the epsilon bar, the something minus epsilon bar. Okay. And so it's clear to see that if the lim inf and the lim sup are equal, then the limit exists. Right? That's equivalent to the limit existing. So it's sort of like a half limit condition. Okay, the lim sup has this sort of half limit condition, right? It's not that you can make all the values within epsilon of lim sup, but that you can make all the values less than lim sup plus epsilon. Okay, right? You can say, I can make, if I want to make them all under this thing, I can find a time past which it happens, right? If I want to make them all under this thing, I can find a time in which that happens. Okay, but I can't control what happens underneath. Okay. Okay. So so let's prove this the second part. So prove with 2. So, well, we're trying to show that right, that we're trying to show that given any x, there's a time past which everybody is lower than that x, right? Well, suppose that for each time, there's somebody who jumps over the bar, right? There's some S of n, right? There's some n bigger than n, such that S of n is bigger than x. Okay. Well, that why is that a problem? Suppose that, so here's our actual lim sup, right? And we've chosen a number x, and it turns out that no matter what time we choose, there is somebody past that time that goes over the bar, right? We choose another time, and there's somebody that jumps over the bar, right? Well, then that's trouble because this thing is supposed to be a subsequential limit. I'm sorry, this thing is supposed to be the supremum of the subsequential limits, right? But we have these infinitely many guys who are more than some positive distance away from it, right? And so they're either going to converge to some finite value that's bigger than this, contradiction, or they converge to infinity, contradiction. Okay. So the Sn is bigger than x for bigger than or equal to x for infinitely many n. But that means that the set of subsequential limits must contain some number, possibly infinity, that's bigger than x, which is strictly bigger than the lim sup. Right? But the lim sup was supposed to be the supremum of E, so that's a contradiction. Any questions? And so, like I said earlier, this is really a characterization of the lim sup. In the sense that any number that satisfies these two properties has to be the lim sup. There's only one number that satisfies these two. Or if there were two, right? If both P and Q satisfy these two properties, we would end up with a contradiction. We'd end up with a contradiction because, and say one is smaller than the other, then we would end up with a contradiction because you have something like this. You'd have P and Q, right? One is smaller than the other, and they both satisfy the second half limit property, right? But then we could say we take this to be our epsilon. Right, half the distance between P and Q as our epsilon, and then past a certain time, everybody would be under here, right? But that would mean that Q is not a subsequential limit, right? So there's a contradiction. Let me quickly try to go through some proofs of limits that Rudin has, and they're kind of cool in that it's a clever use of the binomial theorem. Okay, so Rudin gives a bunch of common sequences and so useful sequences. First is that the limit of 1 over n to the p is 0 as n goes to infinity for all p bigger than 0. Second that the limit of p to the 1 over n as n goes to infinity is 1 for all p bigger than 0. Third, that the limit of n to the 1 over n as n goes to infinity is 1. Fourth, that the limit of n to the alpha over 1 plus p to the n is 0 for p bigger than 0 and alpha a real number. So it goes to infinity. And last, that the limit of x to the n is 0 as n goes to infinity for any x whose magnitude is less than 1. Okay, so here's a bunch of useful limits. The first one I'm not going to do, just read it yourself. It's pretty straightforward. But the second, third, and fourth all rely on the binomial theorem. Okay, which you may recall looks like this. If you have 1 plus x to the n, then that's equal to n choose k, x to the k, k from 0 to the n, where n choose k is n factorial over n minus k factorial k factorial. Okay, I guess I'm only going to do, I only have time to do numbers 2 and 3, which is too bad, but it's okay. It will live. Okay, so let's do number 2, right? We want to show that the limit of p to the 1 over n is 1 as n goes to infinity, right? If you take any positive number and you take successive roots of it, you've probably done this when you were a kid, took a number and took lots of square roots to it, and it always turned into 1, right? Any positive number, you take more and more roots, turn it into 1. Why does that happen? This is the same thing as saying, so let's let x of n be p to the 1 minus n, p to the 1 over n minus 1, so the difference between this thing and the limit. Okay, so we want to show that the x of n go to 0. Okay, right, showing that this thing goes to 1 is the same thing as that showing that this thing goes to, the difference goes to 0, of course. Right? I say, well, look, 1 plus xn quantity to the n is p. Right? Just move the 1 to the other side, get 1 plus x and x of n, take the nth power on both sides, right? We get that, right? But then we use the binomial theorem. We say, well, look, n, sorry, 1 plus n xn. Right? The binomial theorem starts off like, the first part of the binomial theorem looks like this, right? It's going to be 1 plus n xn plus n choose 2 xn squared plus n choose 3 xn cubed plus so on and so forth, right? Right? So this thing, if we throw out all of the later terms, this thing is smaller than 1 plus x to the n, right? So this thing is smaller than 1 plus x n to the n, which is p. Okay, and so we get a control on the size of x of n, right? We get a bound on the size of x of n. X of n is smaller than p minus 1 over n. Right? But then, right, as n goes to infinity, right, as n goes to infinity, we see that the limit of the x of n must be 0. I should say I've only done it in the case for p bigger than 1. Okay. Only done in the case p bigger than 1. But it's easy to flip the argument to get the case p less than or equal to 1. Sorry, humor me just for 1 minute longer. Sorry. And I'll do the second one, the third one really. So we do the same thing, we do a similar thing for number 3. So let x sub n be n to the 1 over n minus 1. Okay, you say, okay, 1 plus x over n to the n is equal to n, right? And maybe you think, we can do exactly the same sort of argument and say, well, this is going to be less than 1 plus n xn, right? And maybe that will give us some sort of bound on x sub n. But as you see, it doesn't work out, right? Because if we try to get a bound on x sub n like this, you see what happens. We're going to get n minus 1 over n. All we get is that x sub n is smaller than this thing. But as n goes to infinity, that just means that x sub n is smaller than 1. That's not good, right? We were hoping to make sure that x sub n is 0, right? Here, this was good. As n went to infinity, this thing went to 0, and so x sub n was squashed between 0 and 0. It had to be 0, right? But here, we don't get such a thing. But we just use the second part of this. We'll use, instead of these terms, we'll use this term here. Okay, well, this is n minus 1 over 2 x sub n squared, right? So n choose 2 x sub n squared, right? And then that gives us that x sub n is smaller than the square root of 2 over n minus 1. Right? Divide both sides, right? We've got this thing less than equal to n. Divide both sides by n, right? Divide both sides by, multiply both sides by 2 over n minus 1, and then take the square root, right? And we get this thing. We get this bound. But this is a good bound because as n goes to infinity, we see that x sub n goes to 0 again. So x sub n goes to 0 again. Okay. So this is a cool, it's clever how he uses the binomial theorem to get the bounds that are needed. Okay. And this one, actually, he uses the general term of the binomial expansion. So he uses like the kth term of the binomial expansion to get it. So I encourage you to read it. Okay, that's it for today.